All right, so now we're going to start talking about these pericyclic reactions. And the first one is this Diels Alder reaction. I actually broke this into two parts. One, because it's a little complicated, and two, because I can guarantee you it's going to be on the ACS exam. Always is, okay? First, just in general, we're going to learn about three different types of pericyclic reactions. The Diels Alder is the first. They always have the same four characteristic features. The first three are the most important, okay? The mechanism is concerted, right? So when we're going to be doing our curvy arrows and jumping electrons around, it's always going to happen. Each jump is going to happen in a concerted fashion, meaning you're going to do all the jumps at the same time. Okay. The mechanism is going to involve a ring of electrons. So what we're going to see is the electrons are going to be kind of jumping around within this ring. And the transition state is cyclic. So 2 and 3 are kind of related. But yeah, there's going to be this sort of circular movement of the electrons that's going to be common. Because of that, the transition state isn't charged. So the polarity of the solvent generally doesn't have an effect on the reaction. To be honest, practically speaking, that's not one you need to remember. The top three are really important, though. They're going to let you know that you're doing everything right for these reactions. Okay, so the first one we're going to focus on is again the Diels Alder, which is a cycloaddition reaction. What we're going to see is that there's going to be a decrease in the number of pi bonds that we get from our reactants to our products, and an increase in the number of sigma bonds. Okay, so this is going to be one of these circular reactions where pi bonds are being broken and new sigma bonds are being formed. Okay, so what does that look like? What's going on here? Okay, so this is a good example of a Diels Alder reaction that would take place between, it's always going to be a diene and what's called a dienophile. We'll talk a little bit more about what makes a good dienophile now. First of all, it has to have sp2 hybridized electrons. Okay, so for these Diels Alder reactions, what you're going to do is, again, you're going to move your electrons in a circular fashion, and you're going to make sure that you're connecting pi bonds to sp2 hybridized carbons. Okay, so that pair of electrons is going to jump there. This pair of electrons is going to jump here, and this pair of pi electrons is going to jump here. Now, what does that do is it forms two new sigma bonds, right? In particular, with this jump here and this jump here, we're forming new sigma bonds. And we're moving a pi bond. So what does the product of this reaction look like? It looks like this, okay? So take a second using these arrows to convince yourself that you can understand how the left-hand side of this image leads you to the right-hand side, that you can tell which bonds are being broken, which bonds are being formed, etc. One of the things that I want to point out is if you look at the book, how the book sort of does this same image is it has a tendency to put the heads of the arrows at the new bonds that are being formed. I don't like to do that because it's really easy to put it in the wrong place. It's important to remember that this pair of electrons doesn't just jump down here. It reaches all the way over to this carbon. Well, that's way too big. To this carbon, and that's how you get that new bond that's formed. If you do it the way that the book does, it's just really easy to make a mistake. And I'll show you an example of that in a second, okay? But this is this cycloaddition reaction, in particular, this Diels Alder reaction. These are called 4,2 cycloadditions. So let me just show you where that comes from real quick. The bonds that are being formed in this reaction are highlighted in blue. Notice how on one side there are 1, 2, 3, 4 carbons, and on the other side there are 1, 2 carbons. Okay, and then again, just to sort of hammer this home, let me actually get rid of these arrows and do my own. This is how I want you guys to do it. What are you going to do? You're going to move your electrons in a circle. You're going to make sure that the base of your arrow is at a pi electrons and the tip of your arrow is at an sp2 hybridized carbon. Right? So this reaches over, grabs that. This reaches over, grabs that sp2 hybridized carbon. This pair of pi electrons reaches over, grabs that sp2 hybridized carbon. Okay, why does that need to be the case? Because again, just sort of looking at this image of conjugated p orbitals. Now we're talking about conjugated p orbitals that originally are on separate molecules, but it's still the same name of the game, right? They're all in this nice line, which is why the electrons are able to move in this fashion. Okay. Again, just to sort of illustrate, remember one key aspect of these pericyclic reactions is the circular transition state, right? The electrons are moving in a ring. I guess something else that could be stated, it doesn't matter, at least at this point, whether you were to draw the electrons moving clockwise or counterclockwise would actually be the same. So let me just convince everybody of that real quick. Get rid of these. So this would have been having electrons moving in a clockwise fashion. Could have done the same thing as long as you stick with those rules where the base of the arrow is at the pi electrons and the tip at the sp2 hybridized carbon. And so you guys can convince yourself that that would have led to the same product. Diels Alder reactions, they take place between a diene and what's called a dienophile. For right now, the only requirement for a dienophile is that it has to have a pair of pi electrons. I'm going to complicate things in the next slide, the next lecture, sort of talk about what makes a good dienophile, what makes a bad dienophile. What I really want to focus on for this lecture is just being able to figure out, given two substrates, what's the product, and given a product, what would be the retro Diels Alder synthesis or what product going the other way, right? Because that's, I think, the hard part is, in general, in this semester, one of the hard parts is that the reactions that we learn about produce ugly looking products, really complicated looking things. So being able to figure out which bonds are being made and which bonds are being broken is a little bit harder than it was last semester. So that's going to be my focus for this lecture. And then we'll go into a little bit more in depth about what makes a good dienophile and makes a really favorable Diels Alder reaction. Okay, so first of all, if in terms of starting out with our substrates, we have 3 pi bonds that are being broken. And on the product side, one of those pi bonds are going to be formed as well as 2 sigma bonds. So that's how we have the net loss of -2 pi bonds and +2 sigma bonds that we learned about on one of those first few slides. Again, the key here is where are those new bonds being formed? So let's take a look. Here is my diene, and here would be my dienophile. And now can you predict for me what the product of these reactions would look like? Okay, so this is why I think it's a little bit risky to just draw the tip of the arrow to where the new bond is going to be formed, because I feel like a lot of people would do something like this, and that's wrong. Okay, remember that the new bond that's going to be formed isn't going to be here because this carbon is not sp2 hybridized. So instead, that's why I tell you to do it a little bit different from the book. You're going to draw this pair of carbons starting at the pi electrons, right? The base of this arrow is at the pi electrons, and the tip of this arrow at an sp2 hybridized carbon. You're going to do the same thing for the next set of pi electrons going to this sp2 hybridized carbon, and then this pair of electrons going to, whoops, I almost broke my own rule, going to this sp2 hybridized carbon. Okay, so good idea to pause, see if you can give me what the product would look like given this mechanism here, but that's going to be the assignment for this particular lecture, is just given a set of substrates, what's the product? Given a product, work backwards retrosynthetically and tell me what substrates you would need to generate that. You'll notice that we're always going to produce 6-membered rings for the Diels Alder reactions. So in this case, and then over here, I guess I don't really, well, sure. Let's do the stereochemistry view. Since they're symmetric, if you just left it like this or like this, that would be fine. To hammer home, we can use our dashes and our wedges to show that one of those methyl groups is going to be sticking up, the other one's going to be sticking down. Okay, but this would be the product of this particular reaction. Which bonds were being formed? Well, this pair of electrons formed this bond, and this pair of electrons formed this bond. And then, of course, my new pi bond was formed when this pair jumped over. Okay, so that would be that. All right, so just being able to be given a pair of substrates and figure out what the product of the Diels Alder reaction would be, that's going to be the hard part for this chapter, or for this lecture. Let me clean this up so it's prettier. It's been a while since I've drawn my hexagons. I feel like I'm slacking here. That is not much better. Anyways, you get the idea. Okay, so now working backwards, right? We got to figure out which bonds which are my newly formed bonds, so I can sort of work backwards here. Okay, so let's take a look at our product here. Notice that from where the new pi bond is, 1, 2, 3, between carbons 2 and 3 away is a new bond that was formed. And likewise, if I go the same direction, 1, 2, 3, between 2 and 3 is another one. So let's just apply that same thing over here. 1, 2, 3. So this would be a new bond. And 1, 2, 3. This would be a new bond. Okay. So that means that my two substrates well, so then I guess we got to sort of even go back a little bit further and figure out what else would happen. So now this component here, this was all by itself. What is it missing? Well, it's got to have a pi bond, right? So this is just, CH2, CH2. That would be this component right here in red. My other one, if I'm going to start putting it together, looks like this, right? All I've done here now is sort of separated this at those broken bonds. I need to then go in and fill in with the proper pi bonds. Where are those pi bonds located on this substrate here? Right, so notice that your newly formed pi bond is located between where your two original pi bonds were. So that means that my diene would be this right here. Okay, so this would be between this ethene and whatever the heck that guy's called. Okay, so that's sort of the goal for this chapter, is being able to take two substrates, create a product, or given a product, work backwards to figure out what substrates we need. Last thing we're going to talk about is the fact that these are stereospecific reactions. So you'll get a particular conformation depending on the stereochemistry of the dienophile that you use. So for example, if I start out with a cis dienophile, that means that I'm going to end up with a cis cyclohexene, right? Or where my two substituents are located on the same side once that ring is formed. Likewise, if I started out with a trans dienophile, I'm going to wind up with a trans cyclohexene actually. Again, if my groups on my alkene were on opposite sides, that means that they're going to be on the opposite sides when the ring forms. Notice that if this happens, you have to include both enantiomers, right? Unlike this compound here, which is meso, this compound here actually does have an enantiomer. Okay. Last thing is that alkynes, all we said for, at this point, all we need for our dienes, our dienophiles is that they have a pi bond. So alkynes can also be dienophiles. And then let's go ahead and draw our reaction mechanism. So this base of the arrow is at this pi. Now the tip of the arrow is at an sp hybridized carbon. It still has the p lobe though, so it doesn't really violate the rule. This pi electron is going to come down form here in this one. Oops. Going to come here. And notice what that does is I'm left with a double bond. My newly formed bonds are still located here and here. Remember, they were that 1, 2, 3 rule. So 1, 2, 3, 1, 2, 3, still located between carbons 2 and 3, counting away from that, that double bond. But now I have a double bond here. Basically, this pair of pi electrons never left. It's still right there on my product side. Okay, so alkynes can also be dienophiles. Last thing about these Diels Alder reactions, and this is something that I said before, they require, you actually might have noticed when we were doing all these things, right? This is just 1,3-butadiene, but it's drawn specifically in that S-cis conformation. You need to have an S-cis conformation in order for a Diels Alder reaction to occur. And remember that the S-trans conformation is usually what's preferred, right? Especially if you have a straight chain alkene rather. Remember we talked about this, there has to be this energy barrier that's overcome in order for the S-cis conformation to be adopted. And if you have a big bulky group, so for example, if we started out with something like this, that means that these two methyl groups would be right next to each other. That's not going to be a good substrate for a Diels Alder reaction because it won't be able to readily adopt that S-cis conformation. The sort of more extreme end of it would be, let's take a look at this compound here. Notice that it is locked in the S-trans conformation. There's nothing that this can do. Because of this ring structure, it can't rotate about that bond. That can't happen. And so you're going to have no reaction that occurs between these two compounds because it can't form that S-cis conformation. And on the flip side of that, if you have something like cyclopentadiene that is locked in the S-cis conformation, right? Those two double bonds are locked kind of in that conformation. That will very readily react in a Diels Alder reaction. In fact, cyclopentadiene is a really common substrate for these types of reactions. If we were in the organic chemistry lab, we would actually use cyclopentadiene. It's pretty unstable, so there's no way that I can get it home to you guys, but nonetheless. And this just brings home one more point that I want to one more thing that I want to show is these reactions will often, especially if you start out with a cyclic pentadiene, will form what are called bicyclic compounds, meaning that you have two rings connected to one another. So these are bicyclic right here. Notice this carbon here is the one that's pointed up there. These two are the ones that are newly formed. And this guy here was your original sigma bond in your dienophile. So if I wanted to do my reaction mechanism here, kind of just like before, but now I've formed a new 6-membered ring, but I still have that bridge, right? Where the tip is that carbon that I've colored in green. Okay, so these are these bicyclic compounds. Again, one of the things that I was sort of warning you about is we're not really doing too much different from last semester. We're just learning new functional groups and learning the reactions. But oftentimes in the second semester, the products that are formed are just uglier. They're harder to keep track of what's what. And this is a great example of these bicyclic compounds.